trajectory shown by the smoother curve. And so by this means, you can extract not only this ratio, but now you can isolate from that ratio the product of the equilibrium constant for the alkane absorption times the rate coefficient for the rate limiting step. And when you put all of this together, I'm going to turn to this side now, you discover some interesting things. First of all, from using UV visible spectroscopy, you get this product, which is the effective or apparent rate coefficient for oxidative dehydrogenation. And it's going up with the loading of the catalyst expressed in units of vanadium per square nanometer. And it's essentially the same, at least in the same order of magnitude, as what you would have measured from steady state kinetics. So that's satisfying because these are two independent ways of looking at the overall rate of reaction. But in addition now, we can extract the rate coefficient for the rate of reoxidation of the catalyst. And notice that this factor here of 10 to the 5th multiplies these numbers here in the table. So the teaching here is that not only can we get an independent check on the rate coefficient for the formation of the olefin from using spectroscopy, but we can also now isolate the rate coefficient for reoxidation. And these rate coefficients differ by a factor of 10 to the 4th to 10 to the 5th. So in fact, we confirm the notion that reoxidation is very rapid. We also can find out by taking the ratio of these numbers here, the fraction of sites which are truly active. This measures the real activity, this measures the apparent activity, because we count all the vanadiums. And by this means, we discovered that something between 60 and 70%, only 60 to 70% of the total number of sites are really active. So this first illustration, I said this is the longer one, shows you how by using multiple experimental techniques, one can dig deeper and deeper into the kinetics of a complicated reaction and look, in this case, at both the reduction and the oxidation parts of the cycle and get a full picture. My second example is chosen to show you that if you apply modern techniques of quantum chemistry, notions of transition state theory, ideas about reaction mechanism, that you can get a lot of detailed insight into this simple reaction of N2O decomposition on the catalyst iron ZSM5. So I summarize here what we know already, that is one of the more efficient catalysts for this reaction. Experimental studies show that the kinetics are very simple. They're first order in the reactant, and that you can extract an apparent rate coefficient with a pre-exponential and activation energy. Where the interesting points come is that if you look at the experimental literature, there's a broad diversity of numbers that you'll find for the pre-exponential factor and the activation energy. The activation energy is spread out over 30 kilocalories per mole from very good experimentalists, so there's an issue of what's going on. And then there are indications in the literature that water inhibits the reaction and NO accelerates it, so they have opposite effects. And the question is, why is this so? And then there's also been lively discussion in the literature about the nuclearity of the active center. Does it have 1 or 2 iron centers? And if it has 2 versus 1, how different in activity are these? So we have addressed this from the standpoint of theory with the idea of identifying the mechanism, determining the rate coefficients for all elementary steps, explaining why water inhibits the reaction, but NO accelerates it, explain the reported variation in the pre-exponential factor and activation energy, and look at the role of cluster size over here. So I'm not going to go into the details of how we do this. This would be a talk unto itself. But I will just show you that here is a typical cluster for a single iron atom center. Here's its relationship to the zeolite, ZSM5. And on a larger length scale, here's the network structure of the zeolite itself. And what we're going to look at is how does N2O come in and interact with the center, and how do the products of that interaction then convert ultimately into nitrogen and oxygen. And I'll just say that in order to do this kind of work, you have to look at some maybe 50 to 100 elementary steps. This is a huge amount of computation. Sometimes transition state searches take us days to a week to find one for one elementary reaction. After that, the post-processing of the data is very quick. And what we end up finally with, after you've sorted through all of this work for the case of the monomeric center, is shown here in this cartoon. This is the as-synthesized center, and what you would see by XAPS. It's completely inactive, but you dehydrate it, taking total energy uphill 43 kilocalories per mole. You'll get this monoxo structure, and this is active for the decomposition process. If you follow your way through this pink ribbon, that ends up with this interesting structure where you have a dioxo and a monoxo on iron. This is very unstable. That releases the oxygen, takes you back to the beginning. So we have put together this story with the rate coefficients for all of the pieces shown on this network. And as kineticist, then just integrated the equations. And before that, I'll show you the rate expression that you can get. It's consistent with experiment. It's first order in N2O. The apparent rate coefficient is anything but simple. It's shown over here. And hidden in here is a dependence on water. It was not obvious when we started that there would be this dependence. And as I'll show you, this water dependence provides the explanation for the huge disparity, things that experimentalists, including ourselves, have reported. But before we get there, I'll just remind you that this approach works very well. Here's the consistency between experiment and theory. They're perfect. This is with our own data. We've also looked at data from Europe, from the group of Pringruber, and we get equal kind of comparisons. And we learn over here that what is happening as you raise temperatures, not only are all the rate parameters getting bigger, but the catalyst is getting more active because you're throwing water off of it. You're taking the iron from its inactive state over here, involving this dihydroxyl, and converting it into a mono, and dioxygen forms over here which are catalytically active. So the catalyst becomes more active as you go to higher temperature. And this is true not only for steady state data, so we get a good fit, but we have also transient response data here. Here we've taken the catalyst in its resting state, and then we put pulses of N2O over it. We follow the burst of nitrogen and then a little bit of oxygen. We're right at a temperature where at the threshold where you can see steady state activity. And so the first thing that happens is that N2O decomposes and leaves oxygen behind on the catalyst. And the temperature is low enough that the release of that oxygen is sluggish, and we don't see it right away because we have to have a second oxygen come in and combine with the first. But if you wait long enough, you can begin to see the first traces of the steady state activity. And so you see the data points and the solid lines here represent our theoretical calculations with no adjustment in any of the parameters. So here's an interesting story. You take all of the data that are in the literature for N2O decomposition. You cross-plot the pre-exponential factor, excuse me, and the activation energy, and you find that there's a considerable amount of disagreement. You look at the black points here. This is all of the available data. But there is a pattern that the points fall along this diagonal over here. So now we plot our calculations for the monomer in the black line and the dimeric iron structure in the green line over here. And we find that the only parameter that is varied here to make the line is the water content in the stream going up to the catalyst. And that accounts for the spread and certainly the angle over here, and suggests that what people have done unintentionally, because of the small amounts of water involved, is work with N2O streams having different amounts of water. It was an uncontrolled parameter. But once you recognize it, you capture that effect over here. And you see that the monomer is somewhat more active than the dimer. It's a factor of 8, not very large. But if you look at the difference between the black and the green line, it captures most of the data. The few data points that are below tend to be from catalysts that were overexchanged, in which one made small particles of Fe3O4, which we know is not catalytically active. So the number of iron centers was overcounted, and if we knew the fraction of the oxide that was there, we could back correct, and the data would fall within the band. Okay, and one last point on this example. Carl Lund has reported, and others have reported, that if you add a little bit of NO now into the catalyst, you increase its activity, particularly at low temperatures. And this has been intriguing as to why this is so. So when we carry this work further, we found that what NO will do is undo the harm of water. So with water, you make the dihydroxide, you put a little NO in, and you make this monohydroxide shown here in pink. And it turns out that this monohydroxide is active enough that it can take N2O to nitrogen and oxygen, and in the presence of NO. It's complicated here. I'm not going to go through the cycle, but you have actually a dark blue and a light blue cycle that work together, and they involve using NO. In the course of events, NO is converted to NO2, but the NO2 is then consumed again. So you cycle between NO and NO2, but at the end of the day, what you do is take N2O to oxygen and N2. And I show you here how this works in the end. What happens is that if you take, say, a fixed partial pressure of water, here 1 ppm, and you start increasing the amount of NO you put into the stream, you can calculate what would be the apparent Arrhenius plot here. And so here with very little NO is what you would have with 1 ppm of water. You now add NO. Sorry, this is the case that we would have with no NO. It's the bottom case. I was backwards here. You add as much as 100 ppm of NO, and now you get the black points over here. So this is the low temperature regime, and in this low temperature regime, you get quite a boost by adding NO, as much as a factor of 10 to up to 100. And you reduce the apparent activation energy by as much as 20 kilocalories per mole. By the time you get up to 750 Kelvin, you've pretty much run out of N2O, you've converted it all. And if you go higher in temperature, you discover now that the NO is starting to have an inhibiting effect because it's blocking sites where the N2O needs to get in and decompose. But for low temperatures, we see that theory has helped us understand what is this positive effect of NO, and how does it compensate for the effects of water. Third example, again, something different. We're going to talk now about partial oxidation, but this time with methane, and we're going to go to formaldehyde. And this is a reaction that happens on very low weight loadings of molybdenum on silica. And I'll show you here in a moment that the first product is 100% formaldehyde. As you try to push this reaction, formaldehyde starts to decompose to CO and water. The hydrogen comes off and oxidizes as water. Get all the pieces up here. So in the literature, it's been shown both for vanadium silica and, for our case, molybdenum silica, that if you stay in this regime, here shown in red, where you have isolated molybdate units, so having 1 molybdenum per center, that the catalyst has essentially uniform activity. And so we made a catalyst with about 0.4 molybdenum atoms per square nanometer, put it on silica, and we see that if we keep the contact time real short, we get 100% formaldehyde. So it's only this first step. There's no pathway from here to here directly. But of course, if the contact time is increased, then we get a reduction in the formaldehyde selectivity as the rate of reaction goes up. But we're only going to look at this front end, and the questions we're going to ask is, how does this chemistry occur? And first of all, what is the structure of the catalyst? So in the literature, there's been a very lively debate by experimentalists largely as to whether you have what are called monooxo species, so molybdenum here, 1 doubly bonded oxygen, 4 oxygens connecting you to the silica, or is it dioxo species where you have 2 molybdenal oxygens and only 2 connections back to the support? And arguments for both structures can be found. If you do the quantum mechanics, you discover that by itself isn't going to answer the question because these are very close in energy to each other, and a little bit of temperature difference and water content difference can shift you from one to the other. So what convinced us was combining theory with experiments. So what I'm showing you here in the upper panel is our Raman spectroscopy, shown in the black. These are the data points over here. And simulations of that Raman band for both the mono and the dioxyl structure. And the only one that agrees with the experiment is the one for the dioxyl structure. Now that by itself wouldn't be very definitive because you can argue about the calculations, how accurate they are, a number of points. What is more convincing is this lower panel, where I show you in black the experimental X-abs pattern, which I'm outlining here. And then what we've done is we've taken both of these structures, which we calculate, and we've done a simulated scattering using the FEF8 code. And the simulated scatterings are shown in red. Here you see very nice agreement for the dioxyl species. You can even see the backscattering here from the molybdenum to the silicon, not only to the oxygens, which are the first two peaks. And if you do the same exercise for the monoxyl structure, you completely miss the boat. You get one peak that's in the right position, more or less, but the intensity is completely wrong, and you don't capture the intensity here at the higher distances. And just to push this a little farther, we've looked at taking this structure and reducing it. By careful reduction, we can take only one oxygen of the two up here off, and then we can put it back stoichiometrically. And we see that when we go from the oxidized to the reduced center, again, we capture correctly what we see experimentally. The mismatch here is really an artifact of the baseline subtraction, which often occurs in the workup of X-abs data. So now, having convinced ourselves that we have an oxidized center that looks like this and a reduced one like that, we've examined various ways in which one could take methane to formaldehyde. We've looked at something like half a dozen scenarios. The only one that finally agrees at all with the kinetics that we have found experimentally is the one I'm showing you on this slide. So we propose that we have a reversible redox over here. Oxygen will absorb reversibly to make this peroxyl structure. Methane will interact with that to make a methoxide and a hydroxyl. So we're basically adding methane across this bond here of the dioxyl. And then there's an intramolecular transfer of a hydrogen atom from here to here. So now you have adsorbed water, absorbed formaldehyde, and those come off fairly easily, and you're back to the beginning of the cycle. And so the difficult part here, the one with the greatest free energy of activation, nearly 54 kilocalories per mole, is this step over here. So let's see how that comes together. So what I show you here is the rate expression that we can deduce from the preceding slide. It's 3/2 order in methane, inverse order in formaldehyde, first order in oxygen. If you pick a set of reaction conditions and you take the values of the parameters shown here from computation, you get an experimental value of 4.2 × 10⁻³ reciprocal seconds and theoretical value of 5.9 in the same units. So fairly good agreement between theory and experiment. And then if you play this out for different partial pressures and different temperatures, here you have the calculated results. The comparison I showed you was this circle point over here. And here you have the experiment. So there's the agreement on that test point. And you see that, yes, theory is not capturing exactly what you have experimentally, but it's capturing maybe 80% of it. And at this level of theory, that's pretty satisfying because the other options for the mechanism and kinetics don't come at even close to this. So we have been able to make some interesting deductions. I'll go back here one slide. We've shown that this is the active center. Very likely the peroxyl that you form at this stage of the chemistry is the important oxidizing species, and it's the addition of methane against this peroxyl that gives you the final chemistry. So the last example, as I said, is one in which we talk about qualitative ideas rather than quantitative ones. For many years, we've been interested in methanol synthesis and asking how could you play with the composition of the catalyst to get more active catalysts. So when we started this more than 10 years ago, we found that several groups were coming to the conclusion that putting copper on zirconia gave you catalysts that in some cases were more active than the traditional copper zinc oxide alumina catalysts, or comparable, but they were more durable and they had other properties that would make them attractive. So we started looking at this. And we did a series of in situ IR studies, both steady state and dynamic. We looked at CO adsorption, hydrogen absorption, hydrogen spillover, and we concluded that in fact this catalyst is bifunctional, that both the copper and the zirconia have a function in catalysis. And let me show that to you by a series of cartoons. So here's the catalyst. It has hydroxyl groups, which you can see by infrared spectroscopy. When CO interacts with these groups, it forms a surface formate. You can see this by infrared spectroscopy. And you can leave the copper out. You get exactly the same band. So we know that CO is going preferentially for the zirconia. Then we know that copper is essential for the dissociation of hydrogen, because if you leave the copper out, you won't get any hydrogen-deuterium scrambling on the zirconia surface, and copper really facilitates this by orders of magnitude. So you have a spillover here of dissociated hydrogen onto the surface. That's shown here. We're spilling over the hydrogen, and it gets up to the formate and hydrogenates it to the methoxide group, which you can see spectroscopically by infrared, and you can see the dynamics of that process. That's relatively fast. And what is slow is the removal of this methoxide to make methanol. In fact, if we follow the dynamics of methoxide and we follow the dynamics in the gas phase of the methanol, they're 1-to-1. So the time constants for these two processes are related, and therefore that methoxide is in fact the precursor to methanol. So what we have asked is, if zirconia is important, not just as a carrier for copper, but in fact in catalysis, what can we do to this zirconia? Could we say play with the phase? Would it matter whether we had tetragonal versus monoclinic zirconia? So the answer is yes. It took us several years to figure out how to make the monoclinic and tetragonal phases with the same surface area, but we finally got that right. And so you have these structures. They're very closely related, monoclinic and tetragonal. You basically take the structure and just twist it a little bit to go from tetragonal to monoclinic. And here what I show you is the rate of production of methanol for the two cases, copper on tetragonal, copper on the monoclinic zirconia. And I'm showing it to you with the same copper surface area in each case. If you go make a comparison this way, you have the same copper surface area, dispersed copper. Not loading, but surface area. And here you see a factor of 8 difference. So that says, indeed, by changing the phase from tetragonal to monoclinic, you get an 8-fold increase. So now the question is, can you do anything else to improve even further? And so you read on in the literature, and we know from the automotive catalysis literature that you can put cerium into the framework of zirconium. So we started looking at that. And so you start with tetragonal zirconia, you add more and more cerium, and eventually the structure goes cubic, and if you go to 100% ceria, you get a purely cubic phase. I'll show you the X-ray diffraction results here, where we start, and in this particular preparation, you can see peaks for tetragonal zirconia, a little bit of evidence for monoclinic. In fact, if I were to show you the infrared spectrum of the hydroxyl groups, they look more like those found on monoclinic zirconia than tetragonal. And this is a consequence of producing a structure that has a core of tetragonal zirconia with a partial shell of monoclinic. So you move on, and this goes through the phase transformations. But more importantly, what does this do for catalysis? So on the abscissa in both cases here is the fraction of substitution of ceria for zirconium. Here none, and here 100%. And you see you can dial in the activity of the catalyst, going from about 1 in the unit shown on the left here to 4, so you get a factor of 4 increase. If you want to compare this to pure tetragonal, it's here. Remember, this is a kind of a hybrid, and pure monoclinic is here. So you do even better than the pure monoclinic. And if you take your worst catalyst relative to your best, you've gone uphill by a factor of 16. And for people who have an industrial bent, the unit of merit here is grams of methanol per kilogram of catalyst per hour. And in those units, this most active catalyst is 420, which puts it in the high end of performance of commercial methanol synthesis catalysts. And it gives you high, this catalyst also gives you high selectivity. We're up at about 98% peak selectivity, which is also very good. The only counterproduct is methane. There are no other alcohols. So we've looked a little bit about what is going on here. We find from in situ Zanes that all the copper is in fact reduced, but 60% of the cerium is not in the +4 state, it's in the +3 state. So cerium goes from +4 when it was first introduced to +3 under reaction conditions. So we create vacancies in the oxide. You look at the in situ infrared, and you see that as you add more and more cerium, things change. You go from having some linear and bridged hydroxides to almost completely bridged hydroxyl groups. And these hydroxyl groups start to interact with CO more and more aggressively as one puts in the ceria. I show you that here. Here are all these catalysts. Here's the CO absorption capacity per square meter. You can see a systematic increase here by a factor of 3. But what's really intriguing is the hydrogen absorption capacity. This goes from 0.3 to 3, a factor of 10 increase. So adding cerium has two benefits, a smaller benefit on the CO absorption capacity and a larger benefit, order of magnitude, on hydrogen absorption. And remember, you need both CO and hydrogen to make this chemistry go. So we're coming towards the end of the story here. Here we plot the apparent rate coefficient for that last step of making methanol. It's this step over here in the cycle versus the cerium content. You notice that goes through a peak. And that is not exactly like the peak in the hydrogen chemisorption capacity, but it's similar. So it's suggestive that what is changing here as we go from here to here is the hidden variable, which is the coverage by hydrogen. That's a large part of it. And here we propose a little cycle to explain how cerium-3 gets involved. It gets reoxidized to cerium-4, and then we go around this redox cycle on the way to making methanol. So I've shown you many results, all relating to how one can take apart complex chemistries happening on catalyst surfaces using both experiment and guided by theory. In the first example, relating to ODH, oxidative dehydrogenation of alkanes, we're showing you that the highest specific activity is observed near one monolayer, where you get these polyvanidates. This activity is inversely related to the band edge energy. And why? The kinetics are well described by a microkinetic model, and that the dynamics of VOX reduction and reoxidation can be understood from UV visible experiments, transient response experiments. Then in the second example, we looked at N2O decomposition on dimers and monomers of iron. We found that both of these are active. We can describe the N2O decomposition in terms of first principles. This is satisfying because if you use a context-free theory, in other words, a theory that wasn't developed for a specific purpose, you should be able to explain what you see experimentally if you have the facts right. And that works in this case. We found that water deactivates the iron, but can be offset by NO. And then in the last two examples, we first showed that methane oxidation will occur on these isolated molybdates, and that they have the structure shown here. They're dioxo, not monoxo. And this is partially reduced in situ. You form a peroxo, and that's what attacks the methane to make formaldehyde over here. And again, you can get the kinetics more or less right from first principles. And then the last example, I showed you that copper on zirconia is a bifunctional catalyst, so both the zirconia and the copper are active. If you add cerium, you can make the catalyst even more active. And that there's a complicated chemistry that occurs, we don't understand it completely, that involves copper as the source of hydrogen, but the oxide as the active component. So many people contributed to this. I've had the pleasure in my 40-year career at Berkeley to work with well over 100 graduate students and nearly as many postdoctoral associates. This is a small subset. Kai-Dan Chen and Morris Argyle were the principal contributors to the story I told you on oxidative dehydrogenation. Ben Wood did the experimental work on N2O decomposition. Andreas Heiden and Niels Hansen, who got their degrees from the University of from the University of Hamburg, were working with Friedrich Keil and myself, did the theoretical work. Mick Oler did the experimental work on the methane to formaldehyde. Shaji Chempak did the theoretical work there. And Ian Fisher, Mike Rhodes, and Konstantin Pokrovsky did the experimental work on methanol synthesis. And I also have to acknowledge the two people I've shown here, the chair of our session and the man who introduced me, Enrique Iglesia, with whom I've collaborated ever since he joined Berkeley in this area of oxidation of alkanes. Arup Chakraborty, now a former member of the Berkeley team, got me started in using theory, quantum theory, and applying it to catalysis. Arup has now moved to MIT. And all of this work was supported by either the Department of Energy or by BP through the methane conversion cooperative. Now, before I end, I want to come back to where I started. I've had the pleasure over something approximating better than 30 years of knowing Michel and Marina. And as I said at the beginning, we've spent many happy occasions together. I just wanted to share two of these with you. So this is a few years back when we celebrated Enrique's receiving the Wilhelm Award in San Francisco. We had a very nice dinner. And here we are just before we sat down to dinner. There's Enrique with his wife, Terry. And most importantly, here's Michel, surrounded by two beautiful women. On his right is Marina, his wife, his love, and his support. And on his left is my wife, who does the same for me, Tatiana, who's sitting here in the front row. I hope you'll get to meet her later, and myself on the right. And then a few years later, this is 2004 at the International Congress in Paris. We celebrated Michel's 80th birthday there. And again, you can see he likes attractive women to be around him. So in this case, it's again Tatiana, and this is Tamara Panov, and here is Gennady Panov. They're close friends of ours from the Berezkov Institute of Catalysis in Novosibirsk. So with that, I bring this lecture to a close. Again, I'd like to thank all who made this possible. It's been a great honor for me to be here, and I'm very happy to have had this opportunity. Thank you very much.
I'm Mayfair from Northwestern University. For isolated molybdenum, silica would not be my choice of the support. The fact that you chose silica, is it because it stabilized the dioxyl molybdenum better than the monooxyl?
No, the reason we chose it is we looked at the literature on formaldehyde stability on various oxide supports. And the one it's most stable on, it's not stable on anything, but the most stable is on silica. It's terrible on titanium or zirconia, it's bad on alumina, and it's best on silica. So that's the reason. And Peter, I think we have
I had a question on the same system. So I think you said that the quantum calculations indicated that the two structures, the monooxyl and the dioxyl, were close enough that it couldn't tell which one was the more stable one. But then in the experiment, you only see one and you don't see both.
Right.
So it seems like somebody's having a problem. Either the calculation's having a problem or the experiment's having a problem. Do you have a notion for which those might be?
Well, if you go to the high temperature, the temperatures at which you do the reaction, actually, the calculations would lead you to expect the dioxide to be the more stable one. But a lot of the experiments are done starting from room temperature in as-prepared materials. So if you start there, you have this ambiguity. If you go to high temperatures, you would expect from the theory to have a preference, not a large preference, but a preference for the dioxyl species. So I don't think we have a problem. I think the most compelling evidence that we have for the dioxyl is the agreement on the structural characterization by XAMS. Okay, I think we're ready for coffee.
Okay, if there are no other questions, let's thank Alex.